All right. 10:06, printing myself out. What we're going to do today then is I want to finish up that section 6.2 about the exponential functions. I want to first go over some more examples of taking the derivative of it, and then do some examples of finding the integral of it, the antiderivative of it. After we go over those examples, I then have just this 2-question quiz. I'll allot 10 minutes if 10 minutes is sufficient for the 2 questions. All right. So let's kind of review a little something first of all here. We're talking about this natural log number e, and it's approximately equal to 2.718. Of course, it goes off to infinity. And we looked at the graph of e to the x, and we saw that as x goes to infinity, the graph goes to positive infinity. So the limit as x tends to infinity of this function is equal to infinity. And then if we go in the opposite direction, the limit as x goes to negative infinity towards the left-hand side of the graph, that it goes to 0. All right. Now, this number is defined in such a way that it has this following property, that the derivative of e to the x power is equal to itself. So when you graph this function and you take a tangent line, the slope of that tangent line, which is the derivative, is going to be the same as the value of the function. So again, the derivative equals the function itself. All right. Okay, oops. Let's go over this way a little bit. Okay. All right. Now, we can use the chain rule, which you learned in first semester. And so the derivative of e to the u power with respect to x, where u is some function of x, is equal to, okay, we repeat the exponent function, e to the u, but we have to use the chain rule and then multiply it by the derivative of that inner function. All right? So I want to do a few more examples here of using the chain rule and doing this derivative. So let's look at the derivative of e to the 5x squared power with respect to x. All right, with the chain rule, we just repeat our exponent function, e to the 5x squared. But we're not finished. We have to then take times the derivative of the inside function, 5x squared. So this gives us e to the 5x squared times 5 times 2 is 10. Lower the exponent, we get 10x. Or we can write it as 10x times e to the 5x squared, like that. Right? Okay. We okay with that example? All right, let's look at another example then of the derivative of e to the secant of x. All right. So with this, it's going to again repeat e to the u power, so that's e to the secant of x. But then with the chain rule, we then have to multiply by the derivative of the secant of x. All right. Now, you're going to be using this and other trig derivatives heavily in these first couple of units. So I'm going to take this opportunity just to go over some things. What do we got here? Okay, the question here is, when doing the homework, can students go directly to the answer without including that extra step that I put there, derivative of what, 5x as part of your work? And my answer to that is yes, you can do that. Okay. I want you to show work, but what I consider some very obvious steps you can leave out, and I'm not going to, as long as I see that you're applying the chain rule, I'm not going to take off for that. Okay, does that help? All right. Okay. Oops. Let's go over anymore. Here we go. All right. So let's look at, okay, derivative of the sine of x. What is that? What's the derivative of the sine of x? The cosine of x. All right. Derivative of the cosine of x. Negative sine of x. Okay. Derivative of the tangent of x. This is going to be a must-know thing. Secant squared of x. Derivative of the cotangent of x. Very good. Negative cosecant squared. Right. Okay, so let's go to the secant here, which is part of our problem. Derivative of the secant of x. What's that? Secant times tangent, right. Secant of x times tangent of x. All right? All right, let's then look at the cosecant. Derivative of the cosecant of x. Right? It has a negative to it. Very good. It's got a negative. Just like the cosine has a negative with it with the sine, but it's negative cosecant of x times the cotangent of x. All right. Let's see. All of these are things that you need to know. All right. That should just be part of your toolbox of things to know. And of course, with any of these, we can use the chain rule with any of these things. So, for instance, let's just look at the secant here. What if we were going to do the derivative of the secant of 11x? All right. So we have to use the chain rule. So we know that the secant derivative is the secant times the tangent, right? So we do the secant of 11x times the tangent of 11x, but we're not finished. We then have to multiply by the derivative of the inside function 11x, which is 11, times 11, or I can just write it with the 11 in front and put 11 secant of 11x times the tangent of 11x. And that would be my answer using the chain rule. So chain rule applies with any of these things. All right, so let's go back here then. Let's go back up here to our original problem, derivative of e to the secant of x. Okay, it's equal to our exponent function e to the secant of x times the derivative of the secant of x, but we've determined then, or we know that the derivative of the secant of x is the secant of x times the tangent of x. Let's get that over a little bit there, all right? So that would be our answer for that one. All right, let's look at a couple more here. Well, I'm going to look at one more derivative. Let's look at the derivative of e to the 2x plus 5, in parentheses, raised to the 10th power with respect to x. Okay. So we see here we have to use the chain rule in order to get this derivative. So how would our derivative here start out?
You chain rule outside of the parentheses.
I chain rule the outside function. So how would I lead up? What's the first thing I'd write on my paper here?
10.
10. Bring down your exponent. Exactly. Write my 10, and then what would be inside my parentheses then? E to the 2x plus 5, my inside function. And then my new exponent would be 9, right? Lower the exponent by 1. All right. But since I'm cognizant of the fact that I have to use the chain rule, then I then have to multiply by the derivative of the inside function. So I have to figure out the derivative of e to the 2x plus the number 5. And so this is going to equal what? 10 e to the 2x plus the 5 to the 9th power times, and then what am I going to get for that derivative of that parentheses there?
The derivative.
Right, because the 5 is going to drop to a 0, so what's the derivative of e to the 2x then? Okay, isn't it 2x? Oh, no. Okay, no. The derivative, okay, let's just look at this. Yeah, that's correct there on the screen. What's on the screen here is 2e to the 2x. That's the correct answer here. I'm glad you brought this up here. In this case, I do not bring down the 2x. This does not equal 2x times e to the 2x minus 1. Okay. We are not using the power rule with this. Notice with this expression, our variable is up in the exponent spot. Okay. So we don't use, this is absolutely incorrect, so don't go there. It's true that the derivative of x to the third, where the exponent is down below, we bring down our exponent and reduce, it's 3x squared, all right? But in this case, we look at the derivative of e to the 2x, and it's e to the 2x, we repeat the exponent function, and then we have to do the chain rule again. So there are questions in which you have to do the chain rule multiple times, and the derivative then of our 2x is 2. Our inside function now is 2x, so it's 2. And so we can kind of simplify this. We have a 10 and a 2 that we're multiplying, so that gives us 20 times, let's put the e to the 2x next, 20 times e to the 2x, and then let's put our parentheses, e to the 2x plus 5, close parentheses, to the 9th power. That would be our full answer. All right. Okay, another thing about how strict am I. Are you strict on notations such as tan, sec, 11x? Yeah, I want it to be secant of, in other words, they're saying, can I write secant of 11x times tan of 11x as tan sec of 11x? I want you to write it out. Apparently, some people, I guess I've never seen that myself, but I guess some people have used that kind of shorthand. Don't do it. So I'm going to put here, no, not okay with that. All right. Okay. So these are some derivative problems here. Let's now do the reverse of integration here with this. So we know that the derivative of e to the x is equal to itself. So therefore, going in the reverse direction, that means that the antiderivative of e to the x is equal to itself. Oh. Plus, I thought it was a church bell coming through. Plus, don't forget our general constant plus c when we have an indefinite integral. All right. So therefore, let's look at some problems here where we're going to have to do u substitutions. All right. And the first one is this. Let's evaluate the integral of e to the sine 3x power times the cosine of 3x dx. All right. So we have to do a u substitution with this. What are we going to select as our u? Sine 3x, not just the 3x. We have to go the whole enchilada, go the whole exponent here, let u equal the sine of 3x. Because we know that the derivative of the sine gives us the cosine of 3x. So therefore, that's what we want to go for our u selection. Now, we then have to find the du once we do that. And so the derivative of the sine of 3x is, okay, the cosine of 3x. But we have to use the chain rule here, then multiply it by the inside function derivative times 3. And then we put dx here. So our du, when I kind of put the 3 in front, is 3 times the cosine of 3x dx. Now, I don't care which way you do this, and I'm going to point arrows in two directions here because this came up in the last class. The way that Stewart does the substitutions is the way that I'm going to be doing the substitutions, all right? So let me put it this way. This is Stewart, and that's the way that you're going to see me doing it. Okay, so we know that du is equal to 3 cosine of 3x. We look up in our integral here, and what we have is just cosine of 3x dx. So to obtain that in this expression here, we need to multiply both sides by 1/3. So I do 1/3 du is equal to 1/3 times 3 cosine of 3x dx. And of course, the 3's there cancel out. So I will then be able to replace cosine 3x dx in my original integral by 1/3 times du. So we're going to do that here. So now our integral becomes, okay, u is equal to the sine of 3x, so we have e to the u power. And then cosine of 3x dx can be replaced by 1/3 du. So I'm going to put the 1/3 in front and put the du afterwards. So does everybody see that with this way I have an equivalent integral with the substitution? Now we find the antiderivative, which is very easy in this case because, let me go back up here. The antiderivative of e to the u du is also e to the u plus the c. All I'm doing is replacing the letter x with the letter u. So going back down here then, the antiderivative of 1/3 e to the u du is going to be 1/3 e to the u plus our general constant. And now I replace the u. And so I get 1/3, I'm at the very bottom here, e. Now the u is sine of 3x plus our general constant c. and that's my antiderivative. All right, now this other way is fine also, but I'm not going to be using it. So we see here in this other way that 3 cosine of 3x dx is equal to du. So if I take my original integral here and I write in du, I've got a 3 here that I didn't have before. So to cancel that out, I need to write in a 1/3. Or another way of doing this, is let's do this. I can write this original integral as 1/3 e to the sine of 3x times the 3 cosine of 3x dx, which is what I have in my, let's get this thing over a little bit more. Right. And then I can replace, okay, the 1/3 gets carried down. This 3 cosine 3x dx is our du. I'll write that down there. And then here's our e to the u. And then we get the same exact thing as what we got there. And then we get the antiderivative as 1/3 e to the u plus c. And then replace the u, 1/3 e to the sine of 3x plus capital C. All right, you get the same result. Okay. All right. Question on that antiderivative. All right, I want to look at 2 more before we go on to our quiz then. The next one is antiderivative of e secant of 2x times the secant of 2x tangent of 2x dx. Sorry, guys. How about that? All right. So again, we have to use a u substitution. So what am I going to want to select as my u? The secant of 2x. So let u equal the secant of 2x, and then we get the du, so we get the derivative. Okay, so as we had seen earlier, the derivative of the secant is the sec times the tangent, so it's going to be the secant of 2x times the tangent of 2x, but we have to also apply the chain rule by doing the derivative of the inside function 2x, so that's times 2, and then we have our dx at the very end. Okay, so this can be rewritten as 2 times the secant of 2x, tangent of 2x, dx. Okay, all right. And then we see what we can do here. Now, what we have in our original integral is secant tangent, sec-tan of dx. So what I'm going to do to this equation here, this is what du equals. I'm going to multiply both sides by 1/2, so I come up with what is actually in the integral itself. So if I multiply by 1/2, I then have my right-hand side is the secant of 2x, the tangent of 2x times dx. But on the other side, I have 1/2 times du. All right. Then we do our replacement here. So I then have, okay, this, I have my e to the u. Now this, the whole rest of this has to be replaced by 1/2 du. So that's our replacement. And now we can get the antiderivative of this. It's 1/2 e to the u plus capital C. And now we replace the u. And so this is 1/2 e to the secant of 2x plus the capital C. Okay? And how can we check that this is a correct antiderivative if we're a little unsure? How can I check that that's correct? Take the derivative of it. So we can always check our antiderivative by taking its derivative. So you can check your answer by, and I'm going to put this in big letters, by correctly finding its derivative. Which means, of course, when you do its derivative, you have to use the chain rule to correctly get its derivative. All right. I actually was going to say, how do we find out the answer is correct? Well, we look in the back of the book and we see if it matches. But I thought, nah. Anyway, but that certainly is one way to find out whether our answer is correct. All right. So I want to do a definite integral now. So this next question has to do with finding the area under the curve. So find the area under the curve of y equal e to the negative 3x from x equals 0 to x equal to 1. All right. Okay, so we know that the area under the curve here is going to be the definite integral from 0 to 1 of our function e to the minus 3x dx. All right. And again, we have to use a u substitution here. So I'm going to pick u is equal to the exponent there, function of minus 3x, and get the du right away from that. So du is equal to, well, the derivative of minus 3x is minus 3, and then put in the dx afterwards. All right. Now we then go back up here and look at our integral here. What we have in the integral is just dx. So what can I multiply both sides of this equation by so that I just have dx on the left-hand side? Negative 1/3, right? Because it's a minus sign. So let's do minus 1/3 du. And then when I multiply on the right side, I get a 1, or just, I don't even have to write that, I get dx. All right. So now I'm almost ready here to do my replacement. What do I have to be careful of with a definite integral where I have those limits of integration when I'm doing a u substitution? What about those limits? Okay, all right. So we have to change the limits of integration. So let's go over here with that. Change the limits of integration. All right. And actually, you'll find, once I tell you how to do it, you'll remember right away that that's how you did it. Okay, now notice in our original integral here, x is 0 and then x is 1. So we put here, u is equal to minus 3x. That's our substitution. So when x is equal to 0, what is the value of u? U is equal to minus 3 times 0, so u is equal to 0, right? So u is equal to 0. I just plug in my x, my lower limit, into my substitution formula here to get my new limit of integration for the bottom number. Now, when x is equal to 1, let's plug this in. U then is minus 3x, so it's minus 3 times 1, and that is equal to negative 3. So, My new definite integral then becomes this. My bottom number is still going to be 0, but my top number, is going to be replaced by the -3. Okay. Does that sound familiar? All right. No, you can have, it'll work out just fine, even though the top number is smaller than the bottom number. It'll work out just fine. All right, but I understand. I knew somebody would come up with that question. Yes?
I have a question. We're going to eventually, I'm interested in being able to down the negative on the integral. When you have a negative integral, we can still put in this, right?
When you have a minus sign, I think what your question is, when you have a minus sign in front of an integral, a definite integral, you can take away the minus sign and flip the order. Absolutely true. That's absolutely true. Okay. So basically, we've got our new limits of integration. So now let's fill in the inside part here. Okay, e to the -3x, that's going to be replaced by e to the u. And then the dx is going to be replaced by -1/3 du. So we have -1/3, and then we have du. All right. Now let's go on and do what you said there, which is perfectly fine. And that way we get rid of minus signs. All right. Or at least we get rid of one minus sign. So what we have here, let me rewrite this. We have -1/3. Let's put that in front here. From 0 to -3 of e to the u du. Okay. Does everybody agree that's what we got? Now, we know that if I've got a minus sign in front, I can get rid of it by flipping the limits. So let's go here on a new piece of paper. So -1/3 from 0 to -3 of e to the u du. I can write that as a positive 1/3. Now this time I put the -3 on the bottom, the 0 on top, of e to the u du. Okay. Right? Okay. Now let's evaluate this. This is 1/3. The antiderivative of e to the u is e to the u. Put our brackets. We go from -3 to 0. All right? So let's plug in the top number. That's 1/3 e to the 0 power minus then 1/3 e to the -3 power. All right, plugging in the limits with be sure we use a minus sign here. And that first expression, how can that first expression be simplified? 1/3 times e to the 0 power. That's just 1/3. E to the 0 power, let's go off to the side here, is equal to 1. Any number to 2 to the 0 power is equal to 1. 1/2 to the 0 power is equal to 1. Any number to the 0 power is equal to 1. So therefore, this first one can just be replaced by 1/3 times 1, or just 1/3, minus 1/3 e to the -3 power. And that's as simplified as I want it. You can certainly distribute, and I don't care about doing this, but you can distribute the 1/3 out and make it 1/3 times parentheses 1 minus e to the -3. I don't care about that, but you can do that, all right? Okay. All right. Okay. How are we with this example then of integrating with the definite? All right. Now, well, I'll leave this up here, some of this up here. Well, actually, I'm going to have to replace that. So what I want to pass out here, and what I'm going to do here for you remote people is this. I'm going to ask all of you guys to, I'm putting here this, we're going to have this is a 2-question in-class quiz. I'm going to ask all of you to get out a blank piece of paper. In class, you don't have to do that. get out a blank piece of paper and put these questions and of course your name on the paper, and I'm going to allow 10 minutes for you to evaluate, give the answers to these two. All right, so we all understand what you guys need to do, and then you hand it in to Bob or Jerry. Okay, so let's give these out to you guys. And for these, you can use your notes, that kind of thing. I don't care, but that's fine. Oops, I'm hearing something there. No, they're not working together. You can use your notes, but work individually. Yeah. You can use your textbook or notes, just work by yourself though. Oops, let's see here. I think we got, yeah, there we are. And why don't we just do it this way, since we want to fit in a little break. Let's figure out that we'll just start again at 11 o'clock, okay? So we'll start again at 11 o'clock. Get a great goal for that one.
It will be starting back up at 11.
Mm-hmm. Yeah.
Oh.
Just found it on the floor. Well, it's not mine. Okay, we're going to start up again, so, okay. I want to go over that second question on the quiz here, because I'm seeing a lot of problems with it. All right. Now, we're going to use the U substitution here for this. So we're going to want the U to be 1 over X, right? I think that helps a little. There, yeah. So let U equal 1 over X. Now, here was a problem that I'm seeing right away here, is getting the du. Basically, with 1 over X, we have to recognize that this is really X to the negative 1 power. All right? That's the same thing. So to get the derivative of this, we bring down the negative 1, and then we subtract 1 from the exponent to give us X to the negative 2 power, right? Just using the power rule. And we tack on the dx. So I can rewrite that a little bit differently here. I can write that as minus 1 over X squared. This is simple exponent manipulation. The negative exponent can become positive if we stick it down in the denominator, and then dx. And then if we look then up here at our integral, this is this is the integral of e to the 1 over x. I can write this as times 1 over x squared dx. I can just kind of separate it out a little bit, right? So we almost have, in this expression here, the 1 over x squared dx. We just have to multiply both sides by a negative 1. So if I multiply both sides of this by negative 1, I get negative du is equal now to 1 over x squared dx. So now I'm ready to do my replacement here. So my integral here becomes, okay, first of all, I have the e to the u, and then the rest of it, 1 over x squared dx, I can replace with times negative du. How are we with this? Which is equal to, of course, we put the minus sign out front. We don't stick it in the middle like that. So my replacement integral here is minus e to the u, antiderivative of e to the u. And we use the fact that the antiderivative of e to the u is e to the u. But here we have that minus in there, so we have minus e to the u plus our capital C. And then finally we replace the u with that, we replace u. And we have minus e, well, u here is 1 over x plus capital C. Oops, where are we there? There. Okay. And that's the answer. Now, what I've seen here on some papers is I've seen some taking the antiderivative of the 1 over x squared. I think I saw that maybe a couple of times. I saw maybe not doing the derivative correctly of 1 over x. All right, right. We have to get that x out of the denominator to properly evaluate it. Okay. So I see a problem there. And another thing that I just saw in a couple of papers, which is a common thing that I have seen, is wanting to keep that integral sign to the bitter end. And you don't do that. Once you have evaluated your antiderivative, you don't need that integral sign. Yes?
Yeah, anything like star fractions, you do the top times the derivative of the bottom times the derivative of the top all the bottom squared.
Wait a minute now. Can you take as, repeat that? You're wanting to use the quotient rule with what? With what specifically? Oh, okay. So in other words, when you get du, okay, so u is 1 over x. All right. That's correct. So the question is, could I, instead of just writing that as x to the minus 1, could I have used the quotient rule? Correct. Let's see what we would get. Okay, so with the quotient rule, the bottom would be the denominator squared, right? X squared. And then it's the bottom times the derivative of the top. Well, what's the derivative of 1? 0, right. Derivative of a constant is 0. Then it's a minus, and then it's the top times the derivative of the bottom. Well, what's the derivative of x? 1. Derivative of x is 1. And then we have the dx right after it. So therefore, what we come up with is 0 minus 1, so the numerator is minus 1, and the denominator is x squared, and we have our dx, and that's our, using the quotient rule, come up with the same du, all right? Now, I guess what I want to say is this: if you're identifying that you need some more help with just the u substitution, then I think you need to go back to where it was introduced in Stewart. I forget what chapter it was in the first semester, and look at that again, all right, and maybe do some problems with that. Because this basic u substitution is going to be prevalent in your take-home quiz, on your homework, on the test, all right? This u substitution, it's important to get it down. You can see me also individually. I'm fine with that, all right? But that's something that we've got to get down before you can really be successful with especially this first and second unit here. Any questions on this example here? I think the derivative is for the most part okay. What I saw, one thing that I did happen to notice here with the derivative is forgetting to do the chain rule again with the 5x, because we have to also at the very end also multiply by 5. All right. Sure. It's going to be well, let's just do it then rather than just write the answer. I repeat my exponent function, e to the 4 secant 5x, and then I'm going to, let's just do it all out here. I'm going to then multiply by the derivative of 4 times the secant of 5x, all right? Okay, so what does that give us? That gives us e to the 4 secant of 5x times what? Okay, well, we've got a 4 here. Now, the derivative of the secant is the sec times the tangent, so we have the secant of 5x times the tangent of 5x, and this is the mistake that I saw at least in one paper. Then, wait a minute, we got to do the chain rule again for this derivative. We've got that inner function, 5x, we got to multiply by its derivative, 5. So what we come up with then for this, we have a 4 times a 5, so if you put your number out front, which you normally want to do, we'd have a 20 out front. 20e to the 4 secant of 5x times the secant of 5x times the tangent of 5x is our final answer there. Okay? So the chain rule is certainly can be done more than once, and you're certainly going to see that where you just go all the way. It's like peeling an onion. You keep going in and into that inside function until you're completely finished with it. Right. Okay. Let's move on here to this next section, section 6.3. And in section 6.3, what it does is it introduces or reviews log functions. We don't actually get into any calculus or derivatives in this particular section. All right. So, 6.3. Oh, let's get this over like this. All right. Is logarithmic functions. And I'm just going to use the abbreviation of log rather than write out logarithmic. Okay. All right. Now, you've seen these functions in college algebra. So, but part of this is going to be a review then of getting you up to date on what these are. Now, so here's some initial facts here. The log function looks like you've got the letters log, you've got a base a, and you've got some expression here. We'll just call it x. All right? And this really equals an exponent, or power. Ooh, I think my pen is losing it, so let me grab another one. Okay, this really equals an exponent, or we could call it a power. All right. So let's look further into this. The log base a of x. What it equals is this. It equals the exponent or power, exponent or power that we need to raise the base a in order to equal x. That we need to raise the base a in order to equal x. All right, so it is an exponent. We're going to go through a couple of examples on this. Now, y equal to log base a of x is the inverse function to a to the y equals x. All right. These two, so it's inverse to the exponent function. The log function is the inverse to the exponent function. It's the inverse to the exponent function. Right. All right. Okay. So one thing before I want to go to some PowerPoint things here, I want to put one note here that's important. We can only take the log of a positive number. We can only take the log of a positive number. I.e., let's say, the log base 5 of negative 3 makes no sense. We cannot take the log of something negative. All right. Okay. Let's see here. I want to go and get a PowerPoint up here. And when I teach college algebra, this is something that this is kind of how I teach logs. I use this concept, because logs can be a little tricky, because they equal exponents, and so it's a little bit counterintuitive at first. I use the spiral. It's a nifty little concept. I think it helps. I use the spiral. Okay, you can see that over there. Good. I can use the spiral, but they can't see what I'm writing. So how about if I put this? I use the spiral to evaluate a log function. And so I'll show what that is in just a second here. All right. All right. Let's see. Let me get this onto the PC projector also. Good. Okay. All right. So this is what I mean by the spiral here. We can go from a log equation to what's called an equivalent exponential equation. So let's look at this log equation here. The log base A of x equals y. All right, that's an equation. It's got a log function in it, all right? Now, this y here is really an exponent for the base. In other words, this y is the exponent or power that the base A needs to be raised to in order to equal the x. So this is the spiral thing. You basically draw on your paper a little spiral. You start out with the base A, you draw a little curved line, gives you to the y, and then you finish off the spiral by going back to the x there. So what this does is, you start with the base A, so you write the base A over here. You're then going along to, you hit the y, and that's your exponent for the base. And then you finish off the spiral with the x there, and you put equals x. These two are equivalent equations, but they're different ways of representing the log, or the value of the log. Okay. So I think let's go through some actual number examples here. Here we're trying to evaluate log base 3 of 81, log base 25 of 5. All right. So let's start with the first one. So we have here log base 3 of 81 equals question mark. We're trying to figure out what it equals. All right, so I put a question mark there. And now what I'm going to do is, by using the spiral, I'm converting that into this equation here. Remember with the spiral, we start off with the base 3. Oops, sorry, didn't mean to do that. We then go over to our question mark, and that's my exponent right here. And then we finish off the spiral at the 81, so equals 81. So this question becomes 3 to what power equals 81, all right? So if you think about it, 3 to the 4th power equals 81. So our question mark is equal to 4. So we can therefore say that the log base 3 of 81 is equal to the number 4. And again, 4 is the power that we raised the base 3 in order to equal the 81. All right, it is the exponent value is a power, the log value is a power or an exponent. Okay, log base 25 of 5 equals what? I put a question mark here. I'm going to rewrite this using the spiral. So, starting off with the 25, I go up to the question mark, so 25 to the question mark power, and then I finish it off equals 5. And so 25, to what power do I raise 25 in order to get to 5? 1/2. Because the square root of 25 is equal to 5. Well, the square root is the same as the exponent of 1/2. So therefore, my question mark is equal to 1/2. And I can say then that the log base 25 of 5 is equal to 1/2. All right. And there's one more example that I have here. Let's evaluate the log base 10 of 0.001. All right, same deal. We're going to say, okay, it equals question mark, I don't know what, and we're going to convert that to the equivalent exponential. So again, I start with my base of 10. I go to my question mark, so 10 to the question mark. Then I finish off with a 0.001. Now, so the thing is, what power of 10 will give me, this is really 1 over 1,000, 0.001. So what power of x10 will give me that small number like that? Well, let's think it through. 0.001 is 1 over 1,000, right? Okay. 1,000 is how many powers of 10? 3. 1,000 is 10 to the third power. So 1 over 1,000 is going to be -3 exponent for 10. Okay, all right. So the exponent here is -3. 10 to the -3 power is equal to 1 over 1,000. All right. And so therefore my answer to this log then, log base 10 of 0.001 is equal to -3. One thing I do want to point out about this example here is when the base is 10, we don't have to write in the base. In this example, if I had left the 10 out in my base, I would be assuming that my base is 10. All right. That's called the common log. All right. So this is a little bit of college algebra back to haunt you. Okay. All right. Now, let's see how these folks are doing over here. Let me just look at something here. Whoops. Oh, I can do this. Sorry. Let's see. Let's do this. Nope. Oh, come on. Okay, there. That's what I wanted. Okay, I don't see any questions from over there. Now, let's go then back to the PowerPoint. And let's start with this current slide here. Okay, now remember I said that the log base a of x and a to the x power, they are inverse functions of each other. They cancel each other out. So they cancel each other out, and therefore they map x to x. They cancel out, x gets mapped to itself. So we have these equations here that when we apply the log function to the exponent function, all we get is the x back. In other words, it's as if we're canceling out the exponent and log here. All we have is the x on one side, so that's what we have on the other side. X gets mapped to x itself. The same thing for if we take a exponent function and apply it to the log function. Again, the exponent and the logs will cancel each other out, and x gets mapped to x. Right. All right. Let's look at what the graph of this function looks like. Because it is the inverse of the exponent function, its graph is the mirror image around the line y equals x. So let's look at this. Here is, let's assume that our base is bigger than 1. So this blue line here is the graph of y equals a to the x power. Remember how when our base is bigger than 1, it gets big very, very quickly, goes up to infinity very fast. All right, so this is our exponent function. Here's our mirror right here, the line y equals x. All right. We can then basically, our log function, log base a of x, is basically going to be a reflection of the exponent function around the mirror. All right? So this is what our log function graph looks like, this pink or red line. Notice how the log function as x, remember, it only can be applied to positive numbers. So notice our graph is only over here on the right-hand side. Its domain is from 0 to infinity, but does not include 0. We cannot take the log of 0. And notice that as it gets closer to 0, it goes down, 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 and goes to negative infinity. The log function, its range is all real numbers. It gets big very slowly, but it can get as big as any real number. The y-axis here is a vertical asymptote. The function goes down, 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 tries to approaches that y-axis, but never touches it. So the y-axis is a vertical asymptote. By the way, I do want to mention to you guys while we're just doing a PowerPoint, that on all the PowerPoints that I put out in class here, I make PDF files of them, and as we go through them, I post them onto Blackboard. So basically on Blackboard, you're going to have my notes that I work out of. Those are going to be scanned. The PDFs that we go through, they're not going to be PowerPoint format. They're going to be PDF format, and so those are easy to get to. And also last time I did start recording the class sessions, and there's also a special folder for that also. So we've got all these tools available for outside of class if needed. All right, what else do we want to talk about here? All right, now what we're going to be primarily interested in for our base for these logs is the base e. So the logarithm with the base e is called the natural logarithm. And it has a special notation, ln. Okay, so this is something that you need to put in your notes if you've not heard of it already, ln, because we're going to be using it a lot. Okay. So therefore, the ln of x is really another way of saying the log base e of x. Except when we have that special base e, that 2.718, etc., we use the notation ln of x. So when you see ln, you can assume that the base is equal to e, even though it's not written explicitly, all right? But it is the base e. Now, we have the same cancellations of the same stuff here with the natural log. The natural log is the inverse of the exponent function with the base e. So the natural log of x equals y is equivalent to e to the y equal x. And you can get this very same thing by using the spiral. With the ln of x here, we have a base e that is not explicitly written. If we use the spiral, we go from e, go to y, so that's e to the y power, finish off our spiral with the x. E to the y equals x. So those are two equivalent equations. Okay, important fact. The ln of x is the inverse function then to e to the x power. They're inverses of each other. That's when we have the base e. So ln of x is the inverse function to e to the x power. And vice versa. E to the x is the inverse of the ln of x. Okay. We have this, because they're inverses, we have the very same cancellation. When we take the natural log of e to the x, we just come back to x. When we take e, raise it to the natural log of x power, we just come back to x. They cancel each other out. Okay. This here gives us a couple of interesting properties that you guys need to remember. Let's suppose we look at set x equal to 1 up here. So what we get here is the ln of e to the first power, or the ln of e, equals 1. I'm just replacing the x with the 1. So right there, I put that in big, bold letters there. We need to remember that the ln of the natural number e is equal to 1. All right? Now, if we set x to 0, we get another one, another important equation here. So so I put 0 in for x here and 0 in for x here, and I get the ln of e to the 0 is equal to 0. Well, as we had mentioned earlier, e to the 0 power equals 1. So this means that the ln of 1 is equal to 0. So that's another fact you need to remember. Any questions on this so far? So when we get to some more, we'll be applying this information some more, especially when we get to the next section. So this isn't the only time you're going to be seeing those particular facts. All right. Now, I'm sure you guys remember from college algebra some certain properties of logs. We can expand log expressions and we can condense log expressions. All right. So let's look at expanding log expressions. If we take the log of two things multiplying each other, in other words, the log of xy, those can expand out as the sum of the log of x plus the log of y. All right. So we can expand a single log into a sum of two other logs. So the product here expands into a sum. And I'm going to go through some examples of this in just a moment. This also, of course, applies to the natural log. The natural log of two things multiplied together is the natural log of one plus the natural log of the other. All right. Because the natural log is just one specific example of a log. We have a similar thing if two things are being divided. If we have the log of x divided by y, we subtract the logs. It's equal to the log of the top minus the log of the bottom. The log of x minus the log of y. And the same thing applies then to the natural log. The natural log of x divided by y is the natural log of x, which is on top, minus the natural log of y. And there's one other thing with expanding. If we have x to a power inside of our log, we can bring, so this is like the log of x to the p power, we can bring that exponent in front of the log. So that's equal to p times the log of x, all right? And the same thing with the natural log. If we have the natural log of x to the p power, we can bring that p in front of the ln of x, like that. Okay. Let me kind of do this with it, and because I want to go through a couple of examples with this, because this might be part of college algebra that you might be a little shaky on. Okay. So let's look at a couple of examples here of condensing. All right, let's see if how much I can get on this screen. I want to try to have this up. Oops. All right. Okay, well, let's see here. Okay, I'm trying to keep both of these things up here. All right, so let's look at a couple of examples here, what we're talking about. Examples. Say you're told to expand the following logarithms. Expand the following log functions. All right. So, say we're given the log base 2 of a times b. Well, that's a product on the inside, so I can expand it as a sum of the individual logs. So this is equal to the log base 2 of a plus the log base 2 of b. Oops, and here we go. All right. All right. Now let's look at, say, the log base 2 of 1/2, a to the 1/2 power. And we're told to expand this. Well, this has an exponent here. I can just bring that exponent to the front. So this can be expanded as 1/2, bringing the exponent to the front, of log base 2 of a, like that. All right. Now let's look at, say, the ln of the square root of a times b. And let's expand this out. Well, we know that the square root is taking it to the 1/2 power. So this is really the ln of a times b raised to the 1/2 power. That's just getting rid of the radical. And the first thing I can do is I can bring that 1/2 out front. So let's bring the 1/2 out front. I'm using that last property. And that's equal to 1/2 times the ln of just a times b. All right? And now I've got a simple product here. I can expand that out as the sum of two ln's. So this is equal to 1/2. Now this 1/2 applies to the whole thing. So I'm going to put some parentheses here. And I'm going to then expand this ln of a times b to the ln of a plus the ln of b, like that. But I have the 1/2 applying to the whole thing. All right. How about something even more complicated that we want to expand? Let's expand the ln of x to the third divided by y squared z to the fourth. So this whole expression here, the ln is being applied to this whole expression. All right. So we get actually to use, I think, pretty much all three rules here when we expand this. First of all, notice I've got a top expression divided by a bottom expression, so I can initially do this. I can expand it out as ln of the top expression, but because I'm dividing, it's minus the ln of the bottom expression, ln of y squared z to the fourth, and let me make sure we understand that there's parentheses around that. Parentheses here. And now let's see, well, certainly I can, in this first expression, I can bring down that exponent into the front using the last property. So I have 3 times the ln of x. But I'm not quite ready to do that yet with this second one because I only supposed to have one single exponent, so I can't do that yet. What I can do with the second expression is I've got the ln of 2 things that are being multiplied, so I can expand it to 2 individual logs that are added to each other. Don't forget the minus sign, though, that I have in the front here. So this is going to be the ln of y squared plus the ln of z to the fourth, like that. I'm just expanding it like that. Now, the last thing I can do here is now I just have a single exponent here. Now I can bring, finally, those exponents down in front. So let's... Oh, sorry. I was trying to get all this on the screen. Okay. So let's get that. And so now we can bring those exponents down in front. So this becomes 3 ln of x. Now minus, I'm just going to do this in a couple steps. You could do it in one step. I'm going to keep those parentheses, and the inside then is going to become 2 times the ln of y plus 4 times the ln of z. All right. And then as my last step, I can then distribute the minus sign to both of the things on the inside. So this becomes 3 ln of x minus 2 ln of y minus 4 ln of z. That's my full expansion of that, right? And I know this is about as exciting as watching some paint dry on a wall, and I get the same reaction with college algebra with this. So thank you for bearing with me on this. Actually, what we're going to just say is something you can look forward to over the weekend. I'm going to save the opposite direction, condensing multiple log expressions into one. I think we'll save that delight for Monday, okay? Because it's almost time anyway, and all that good stuff. Let me see, did somebody here have a question? No. Somebody's typing a message, but I don't know what it is. What is the message? Okay, so anyway, don't forget, this homework is due on Friday. Don't wait until Thursday to get started on it, okay? So I want to start off the semester well, so don't forget the homework. Okay.
I should be able to show you something.
Yes. Yeah, I use it backwards. Yeah.
When you grab this, you should be able to split right there. Bring it even, and not perfectly stick it up half.
Oh, what are we doing? Okay.
So all you got to do is whatever you do. Well, you can do it multiple ways. If you want it full screen, you just pull it all the way up. And then if you want it to the left, you just pull over the left window.
she'll
Or the
hold
right.
on the fence the next year.
Or if you bring it back, we'll take it back.
So how far over do I have to pull it over? Just,
See how that blue thing comes up?
yes.
When you bring it over to the side, it automatically pulls it halfway.
Okay, so let's see here then with this other way. Somehow I've always used the mouse upside down.
Okay.
So what's
Do you
happening?
see your mouse, the clicker? That has to touch the screen.
Oh,
Yes.
oh, I see. Okay, that's the key. All right, great.
Thank you. No problem.
Right. Yeah, exactly.
But it's one of those things that everybody seems to make it wrong, and make sure that you get it right.
Do you check your email outside of, or like on the weekends, or?
Oh, yeah. Compulsively.
Some teachers.
Compulsively.
If it's not office hours
Say-
at school, they're like, I don't know.
No, I need to actually seek professional help for this. But yeah, I'm really bad at checking email.
Okay.
All right.
Yes, that's what I said. She took it already like you did. Now she's taking 25. Sorry, but she had it on early like you did. Okay? She took it, there's a screenshot, and she took it over as paramedic. So she had the exact same class as you did. And she's not doing well because her boyfriend, several years ago, got with her. What? She hasn't always said. Yes.